Welcome to qnawire.
In this problem, we need to determine the velocity of the bullet for which the maximum angle of rotation of the beam will be 90 degrees. So, I have here a sketch of the problem. So, a bullet with a mass mb and velocity vo is fired into a beam with mass m at point B. So, that's what you can see in the first part of the sketch. So, this causes the beam to rotate about point A, as you can see on the last part of the sketch, with angular velocity omega 2 and its mass center to move with velocity v2. So, I've included in the sketch the given value. So, the length of the beam is 4 feet. And then the velocity VO is 750 miles per hour. Then the mass of the bullet is 1 ounce. And the mass of the beam is the weight of the beam, that should be the weight. So the weight of the beam is 18 pounds. So, converting the weight of the bullet to pounds, so the weight of the bullet is equal to 1 ounce. So that is actually equal to 0.0625 pound. Now, getting the mass ratio, so you will see, so using the weight first, weight values, so you will see that the mass ratio is 0.00347772. So since the mass ratio beta is so small, the mass of the bullet will be neglected in comparison with that of the beam. So in determining the motion after the impact. So hence we can express the weight of the bullet in terms of the ratio. So the mass ratio times the weight of the beam. So for the mass, so that would be the same. So the mass of the bullet is equal to the ratio times the mass of the beam. So there. Now, writing an equation for the linear components of momentum. So we'll have negative beta m VO plus 0 equals mv2. So from here we can get v2. So v2 is equal to beta VO. Now, solving for the moments about point B, taking the clockwise direction as positive, so we'll have 0 plus 0 equals, so I omega 2 minus m v2, then L over 2, because the center is at a distance of L over 2 away from point B. So since this is a rod, the equation for the moment of inertia is 1 over 12 ml squared, and given the equation for B2, which is beta VO, so this equation becomes 1 over 12 ml squared omega 2 equals m beta VO L over 2. So from here we can get the equation for omega 2. So omega 2 is equal to m beta VO L over 2 times the reciprocal, so 12 over ml squared. So this would be equal to 6 beta VO over L. So we now have an expression for omega 2. We'll now analyze the motion of the beam at point 2 and 3 using the principle of conservation of energy. So I have here a sketch of what happens in position 2 and position 3. So position 2 is when the bullet strikes the beam, and position 3 is when the beam rose and forms an angle theta m with the vertical. So as you can see in the last part of the sketch. So our reference point is point A. So the equation would be, so K, kinetic energy 2 plus potential energy 2 equals kinetic energy 3 plus potential energy 3. So for position 2, our potential energy is equal to negative mg L over 2, because A is the reference point and the center is at a distance of L over 2 away from A, below A. So that's why we have a negative sign here. And then K2 is equal to 1/2 mv squared, mv2 squared plus 1/2 I omega 2 squared. So substituting here the equation for V2 and the one that we got for omega 2 earlier, and then the moment of inertia, so K2 becomes, so K2 equals, so 1/2 m, so beta VO squared plus 1/2 times 1 over 12 ml squared times the equation for omega, 6 times beta VO over L squared. So simplifying that, so we'll have, so K2 equals, so m beta squared VO squared over 2 plus, so 36 ml squared beta squared VO squared over 24 L squared. So simplifying this, you will see that this is equal to, so 2 beta m VO squared. So that's it for position 2. So for position 3, so our potential energy is equal to negative mg L over 2 cosine theta m. So because as you can see in the last part of the sketch, so the beam makes an angle of theta m. So if we'll get the distance from point A to the center, so that would be L over 2 cosine theta m. And then our kinetic energy here is equal to 1/2 mv3 squared. So to solve for v3, so to have an expression for v3, we can write an equation for the linear components of the momentum. So we'll have mv2 plus 0 equals mv3. So this tells us that v3 is equal to v2, so which is equal to beta VO. Hence, so our K3 is equal to 1/2 m beta squared VO squared. Okay, so now we have the kinetic energy values and the potential energy values. So our equation for conservation of energy would be, so negative mg L over 2 plus 2 beta m VO squared equals negative mg L over 2 cosine theta m plus 1/2 m beta squared VO squared. So, simplifying this, so we'll have 2 beta mVO squared minus 1/2 m beta squared VO squared equals, mg L over 2 minus mg L over 2 cosine theta m. So the left hand side would be equal to 3 halves m beta squared VO squared equals, factor out mg L over 2 times 1 minus cosine theta m. So beta squared V squared equals mgl times 1 minus cosine theta m over 2 times 2m over 3. So, VO. So, beta VO is equal to square root of, GL times 1 minus cosine theta m all over 3. Substituting the values, VO is in miles per hour. So let us convert this first to feet per second. So VO equals 750 miles per hour. So to cancel miles, multiply this by the conversion factor. So 1 mile is equal to 1,609 meters. And then to cancel hours, 1 hour is equal to 3,600 seconds. So this is equal to 1,100 feet per second. Now, substituting the values in the equation for beta VO. So beta VO equals, the value of G in feet per second, 32.2 times 4, then 1 minus cosine 90 degrees, then over 3. So this is equal to 6.5524 feet per second. Then finally, solving for VO. So VO would be the value that we got earlier divided by the value of beta. So that would be 6.5524 feet per second over 0.0034722. And that is equal to 1,887 feet per second.